Assalamualaikum warahmatullahi wabarakatuh and a very good morning.
Waalaikumsalam, Doctor.
Good morning, Doctor.
Good morning. All right, so let's start our class. So, today's topic will be a new chapter, so which we call a phase system. But because last week we doesn't have a class, so let's do some revision. Okay, as usual, so we have this diagram. So going to look at it again and again, so that everybody will get the idea of what is actually we are learning, the whole thing for DSP in this course. Okay, so this is actually the things that we are trying to cover, so which we call a LTI system, and we are actually focusing on filtering application. Okay, so in LTI system, because it is a system should have input, a system should have output, and it should have what we call the impulse response. Okay, for LTI system, this is very unique. So we have impulse response. If it is not LTI system, it's just a system. It is not linear. It is not a time invariant. So you won't have this unique impulse response. Okay, you have a process, but we doesn't call it. It doesn't have a unique impulse response. So it can have an impulse response, but not a unique impulse response. Maybe you will have a lot of impulse response. Okay, but for LTI system, you will have only a single and unique impulse response. So that's why LTI system is very special. So that's why we are learning it, because most of the system is actually using LTI system. Okay, it's easy to design and it's easy to control and everything. Okay, so in this, if we are looking at this diagram, so this is the input. So the process is here based on this filter, and you'll get the output. So, and the process is what we call a convolution. Okay, so how to get the output? You do convolution between input and the filter. So then you will get output. So, and convolution is actually in time domain. And we have seen this several analysis in time domain. So this is analysis in time domain on stability and causality. And then we have seen analysis also in a Z domain for stability and causality. And then, so those are inverse Z transform. And recently, this a few weeks, so we are covering a frequency domain. Okay, so we are using what we call a Fourier transform. And for discrete time, so it is a very specific. So we are using what we call a DTFT. So or this is a discrete time Fourier transform. So previously in the previous course, so actually you are using you are doing a Fourier transform. So the name is a Fourier transform alone. It doesn't have that DT in front. Okay. So just to differentiate between the continuous time and discrete time. So now we call it discrete time Fourier transform. But what is the basic? So we are actually are transforming our time domain signal into a frequency domain, a plot. Okay, because if you are looking here, this is a convolution we have learned, we have covered these properties. Convolution in time domain. So actually what we will get is multiplication in frequency domain. And that multiplication is actually easier to understand and easier to manipulate, to design and to solve a system. Okay, but implementation wise, so we will do convolution, because the implementation is, you should implement it on time domain. So that one is easier. So for analysis, for understanding, for manipulation, designing, so we're going to use the frequency domain, because everything becomes easier, because this convolution is actually becomes a multiplication in the frequency domain. Okay, and we have seen that we can do this a Fourier transform, or transforming a time domain into a frequency domain for input signal, for output signal, and also for the filter itself. Okay, and what is the relationship? As I already mentioned, so these outputs, the y omega, of course this is in time domain, the frequency domain should be y omega. So y omega is actually just this x omega multiply with h omega, right? Multiplication. Time domain, convolution. Okay, and then so today we're going to look at this one, phase. So we have seen on a lot of example in magnitude. Okay, so we will see another example today. Okay, and but today we're going to focus on phase. So what are several systems of this LTI system described by phase? Okay, we're going to look at that one. And the rest will be after that, so next week. Next week, we will cover this DFT. So this is, you can see that this is a DTFT. So next week, so we will cover what we call a discrete Fourier transform. So what is the difference? So now what we are covering is actually discrete time Fourier transform is actually involving the frequency is omega. Okay, so we have 5 types of frequency. Now we are dealing with omega, small omega. And that small omega is actually a continuous value. The time is discrete, but the frequency omega is actually still continuous. DFT, so it will the frequency will be represented by K. Okay, that K is actually discrete frequency. So we're going to look at on how to convert this omega, that continuous omega, into a discrete value of K. So that one will be next week. And then the rest of the class is on designing. So we'll design IR filter, and then we will design FIR filter. Okay, so that one is later. Okay, and then just few things. This one last time. So actually we are already covered until this slide. This is actually from a DTFT properties chapter. Okay, this is a chapter 9. So we will cover up to this slide only. Okay, we're not going to cover this topic, frequency response related to poles and zeros. Okay, the rest from this slide until the last slide. So we're not covering this thing. So what else we have? Okay, still a lot of things, but we're not covering it this semester. But of course, if you are interested on it, so you can always find me and I can show you what are the materials are. Okay, but we are covering until before this topic. A lot. Okay, so this is slide number, I think, 16. So 16 onwards, so we're not going to cover it. Okay, so let's go to our new chapter. So this is called a phase system. Okay, as we have seen. So in a frequency domain, so we have a two plot that we're going to analyze, because in frequency domain, similar to Z domain. So because a Z domain is a complex domain. So in complex domain, we have a real and imaginary value. Okay, so a similar thing in the frequency domain. So actually we have a real and imaginary value. But those real and imaginary value doesn't give us much information. So we need to convert it into magnitude and phase. Okay, so we have this magnitude and phase. And this is what we're going to cover today. So we're going to focus on phase. Right? So in time domain, phase in a signal, so this phase can be seen as a time delay. So that's actually what is the effect of having phase. So if you have a phase in your signal, so actually your signal is being delayed. Okay, so what is it? So this is actually coming from this equation, cos omega n plus phi, because this is, so what is this? So this is, let's get back to, it can be sine or cos, because why we are really interested in this cos or sine, because this is what Fourier did. He has proven that any signal can be decomposed into a series of sinusoidal signal. Okay, so any signal. So this is where, and that's a series of sinusoidal signal means that it is a sum. It is a sum of a sinusoidal signal, and sinusoidal signal can be cos or sine. And so let's get back to this very basic things on. So who did this? So actually Fourier did this. Okay, and then we need to learn everything. So any signal can be decomposed into a series of sinusoidal signal. Right, so that's why we are actually looking a lot on this sinusoidal signal, because this is a theory. Okay, this is the theory. So this is a concept. That's why we are looking at this thing. So it means that any signal, so you can have any signal. So this is actually can be decomposed. Decompose means, so you can have, let's say, maybe this signal, and then this signal, and then this signal. Okay. So it is a series. A series means it is a sum of sinusoidal signal. So what is the difference between this? And of course, this is actually, you can have maybe infinity number of sinusoidal signal. So that's what normally you should have. Okay, an infinity number of sinusoidal signal for a signal. So what is the difference between each of the sinusoidal signal? If we are looking at, so this is where we can put it as a cos omega n plus phase. Okay, this is an example. So we have three things. One is the amplitude. This is a frequency. Okay, this is a discrete time frequency, and this is the phase, right? So we have those three. Frequency, and then this is phase. And yes, we already know this. We have seen this a lot. So, and this is actually an equation in, this is in time domain. Okay, so because we know that this is actually, any signal can be decomposed into a series of sinusoidal signal, and each of these sinusoidal signal is actually representing single frequency. Okay, this one has a one frequency, this one has a single frequency, this one has single frequency, this one has a single frequency. So this is why it gets interesting. So actually we can rearrange, we can sort back this thing, so that we can have a new plot. So where these plots, the x-axis is time. So we can have a new plot, which is the x-axis will be frequency, because we have this sinusoidal signal. So we can sort it back, okay, from the lowest frequency up to the highest frequency. So this is where, when we look at, when we convert it into a frequency domain, okay, so that A, so this is going to be, it is a proportional, how to spell that? Or simpler words, this is shown by magnitude response. Okay, the magnitude response in the y-axis. So it is actually proportional. So if you have A, then the magnitude is actually proportional to the amplitude. And this is phase. So of course, obviously, so this is actually shown by the phase response. The same thing on, we are looking at the y-axis. Okay, and this is the omega. So this is the frequency. So this frequency, so it's actually on the x-axis. So we sort everything back. Okay, we sort everything back so that this frequency is now on x-axis. This amplitude is shown by a magnitude response. And this phase is shown on the phase response. And both magnitude and phase response, the x-axis is the frequency. Right? Okay, so so those are actually the basic. So why we are actually having this sinusoidal signal? Because of Fourier has a theory on it. Okay, so that's what we call a Fourier series. Then, if we are looking at this, so we can actually rearrange the signal omega n plus phi equals to cos omega n plus this phi divided by omega. So what you can see here is actually that phase is actually, it is a delay. So this is what we call a delay. Okay, this is what we call a delay. So why this is important? Because when we do some filtering process later, so we know that our output will be affected by some delay. Okay, if we have some phase. So if the phase is not zero, then it will be affected by the phase. Okay, so but what will be the relationship? So this is actually the relationship. And now we have, so if we have in time domain, this is the time domain, it is simply as convolution between xn and hn, time domain. Frequency domain, so it is a multiplication. So this is where, when I say that everything becomes easier to manipulate and easier to understand, because in a convolution, so this is actually quite difficult to understand what is actually happening here. Okay, so but because that convolution is actually you have a summation, you have multiplication. Okay, so and delay, so that three process. Okay, let's look at this frequency domain operation. So what actually we have is just a multiplication. So you have your frequency response of x omega and frequency response of your filter, which is h omega. Do multiplication. And we already know that this is actually a complex value, right? Complex value, if we expand, so you should have real and imaginary part. Okay, same thing here. So we have a real and imaginary part. And again, because it doesn't have a really useful information using this form. So what is this? So mathematically, so we call this a coordinate form. Okay, coordinate form. So we write it as a real and imaginary. And this one, so we convert that into what we call a polar form. So in polar form, so we can see it is actually rewritten using magnitude and phase. Okay, so how to get the magnitude? Take the real value, square, plus the imaginary, square, and then you square it, you'll get this one. Okay, and this is a phase. That magnitude is multiplied by exponent of j of your phase response. Right? Then we can write this same thing, the magnitude of the filter, multiply with the phase, the exponent to the phase of the filter. And if we do the multiplication here, so what we can see now is, and of course this one you can write it as E minus a j phase of y omega So because this is a multiplication, that magnitude multiply with magnitude, it is still a multiplication. But this is to the power of, okay, exponent to the power of something, the phase. This is exponent to the power of the phase. And this operation becomes summation. Okay. So this is what we can conclude. So if you have a filtering process, so this is actually a filtering process. Why? Because in time domain, it is a convolution. And this is what we call LTI system. Okay, the operation is a convolution. And what we can see now is actually to get your output, so you need to multiply both magnitude. Okay. This is magnitude. Magnitude is multiplied. Phase is sum. Okay. Because by looking at this original formula, so because this is we don't separate it into magnitude and phase, so we just see multiplication here. But after we do some expansion, convert it into a polar form, then we can see that actually the multiplication is on magnitude. But on phase, so it is actually a sum. Okay. So what is the phase of your output signal after some filtering process? So it is actually a sum of the phase in your input signal and the phase of your filter. Right? So we will see some example after this. And we already see several example here for magnitude before. So it is a simple multiplication. Okay, so because that's how we do a filtering. So how do you remove a frequency? You're going to multiply with 0. After you multiply with 0, the value becomes 0. So it means that total remove. If you want to preserve a frequency, so you multiply with 1. So make sure your filter is equals to 1 on that frequency. Okay. So if you just want to reduce, so maybe you will multiply a value between 0 and 1. So that's how we do. That's how we do a filtering. So that's how we remove or preserve a frequency. But other than that, this is actually the effect on phase. What is the phase do to our signal? It will give a delay, right? So it will give a delay. Okay, actually this is the explanation on those things. And in phase system, what we are actually a concern is on what we call a phase distortion. So whenever we are designing a filter, so we need to make sure that as much as possible, so it doesn't have what we call a phase distortion. Okay, so what is a phase distortion? Signal can be understood as the combination of sinusoids of different frequency. If the time delay of this frequency is not consistent, then it can be said that the output signal has a phase. Right? Sorry, this is actually not X. This one's supposed to be YN. So if you have an input signal, let's say this is a very conceptual signal. So we have two frequency here. So this is the first frequency. Let's say the frequency is a 0.1 pi. And this is a second frequency, so which is a 0.5 pi. Okay, this one has a higher frequency. Okay, so a more repetition compared to this one in 1 second. So then let's say this is a single signal. The signal is just it do this and then stop at A, and then suddenly the signal start again at B, but with a new frequency, which is a 0.5 pi. So then we filter this thing. We do filtering on this signal. So let's say we do some filtering on this signal, try to do something on it, and then this is the output that we get. Okay. So let's say this is A. So this is A. So if we look back at this concept, so the magnitude is actually affecting the amplitude. Okay, magnitude is actually we are looking at what will be the effect of the amplitude. The phase, we are going to look at what is the effect on in a time domain, a delay, right? Okay, so we need to remember that magnitude, it will affect on amplitude. Phase, it will affect on delay. Okay, let's see on the first part of the signal. So it starts at 0, and then it ends at A, and then the amplitude is A. No difference at all. Okay, so what do you think? So what happened here? So what does this filter do to this frequency? Okay, so we can have H omega. Let's say this is the magnitude, and this is the phase. So clearly, it doesn't do anything to this frequency. So it means that our at omega equals to 0.1 pi, because the frequency is at 0.1 pi, our h 0.1 pi is actually equals to 1. Do nothing to the amplitude. So if you multiply by 1, A, you still get A. Okay? It doesn't increase, it doesn't decrease at all. And what will be the phase? The phase at 0.1 pi is actually equals to 0. So because let's say this is, it has a phase here, and then no delay at all. So let's say this is no delay, and then this is no delay, the same thing. So it means that the phase will be 0, no delay. So how about this one? So originally it's supposed to start at B. Okay, but now it is start at B plus A. So it's being delayed by A samples. How about the amplitude? The amplitude is still the same. This is still A. So we can conclude that at omega equals to 0.5 pi, our magnitude is actually equals to 1. We do nothing to the amplitude. The amplitude is still the same. Okay? But this filter is actually doing something to the phase. So it has a phase. The phase is not 0 at frequency 0.5 pi. Of h 0.5 pi is actually equals to let's say, so there is something here. Okay, there is something here. So what is the value? So we're going to look at that in our example later. But the phase is not 0. The phase is not 0 because we have some delay. So how many delay? The delay is actually E. So because it should start at B, but at the output, it's being delayed. All right, and this is in one system. So let's say we have a H and this system. So at 0.1 pi, the phase is 0. At 0.5 pi, the phase is not 0. So we have a different phase. Okay, so it doesn't matter what is the value, but this is not similar. So if this is not similar, then we will say that it has a phase distortion. This is what we call phase distortion. If it doesn't have a phase distortion, the phase is supposed to be consistent on all frequency. Okay, so if this is 0, this one's supposed to be 0 also. If let's say this is 0.1, this one's supposed to be 0.1 also. Right? So then it doesn't have phase distortion. So what is the phase distortion? So when we have a different phase on different frequency. Okay. Any questions so far? Before we move to maybe some more example. Before that, some category of system. And this is actually any questions? All right, and this is how we quantify phase. And so we have what we call a phase delay. So we put it as a TP. TP is actually just your phase response divided by your omega. See, this is a H omega. So then divide by omega. Okay, and then we have a group delay. Group delay is actually a d over d omega. So no worry about this thing. In discrete, this is just a difference operation. Okay, means that if you have a two value, you just minus. Okay, so you just do minus. So right, so that one is a TG. So and we call it as a minus d over d omega of that your phase. Okay, no worry about that one. So let's look at this thing first before we move to some example. So in phase system, we already know that LTI system, we already categorize it into two. So one is what we call a FIR, finite impulse response, and then another one is the IIR, finite impulse response. That's how we categorize the LTI system based on its impulse response. And this LTI system can be categorized into a phase system also. So we have three types of phase system. So one is what we call a zero phase. This is a linear phase, and then a non-linear phase. Okay, we're going to look in detail these two, zero phase and linear phase. So we're not going to look in detail on this non-linear. So, but other than zero and linear phase, so it will be a non-linear phase. Okay, so let's go. So this is a zero phase. So when will you have a zero phase system? So zero phase means your TG is actually equals to 0. Okay, and when should you have this one? So Hn must be symmetry or even signal. Then you will have a zero phase system, or anti-symmetry, which is the odd signal. So either it is a symmetry. So we have seen this because FIR. So we have type 1, type 2, there's a type 3, and then a type 4. Okay, so actually this is from FIR. So, and all this special FIR, type 1, 2, 3, 4. So this is actually zero phase system. Okay, so that's why this is quite special. It is a special because it has a zero phase. Zero phase means if you apply this filter, so you won't have any delay at output, which is perfect. Okay, because we doesn't want to have any delay actually, if possible. Okay, but so how to get that? So we can use what we call a zero phase system. And where can you get this system? So it is from FIR type 1, 2, 3, 4. So where it is a symmetry or anti-symmetry, either it is an even or odd system. And this is an example of symmetry. So we have seen this. So this is an example of it. We have 5 samples here, starting from -2 up to 2. And where is the symmetrical line? At 0. So the symmetrical line should be at 0. And this is the anti-symmetry. The symmetrical line is also at 0. And then at -2, so the value is -2, but at 2, the value is 2. Okay, this is what we call anti-symmetry. So these 2 types, and actually we have 4 types. So it will have a zero phase. And this is actually it's already fixed. So this is actually the phase. So the phase for even and odd signal are constant value as follows. So this is constant value. So you just, whatever it is, you should have this one. So if you have a zero phase system, so this is your phase. It's already fixed, right? So it will be 0 if your H omega greater than 0. So because if it is even, if you still remember the symmetry properties, if it is even, H omega even is actually just equals to H omega, you will only have a real value only. So you won't have any imaginary value. And this is oppositely H omega odd. So you should have the imaginary only. Okay, and the real part is actually a 0. Okay, because you only have one component only, one is only real, another one is only imaginary. So actually you are having a fixed phase response. Okay, so, and even though this is a 0, pi, minus pi, so actually this pi and minus pi is actually considered 0. So there's a manipulation on some maths here. Okay, so that's why we call it 0. And the same thing here. So because this is there is some shifting a bit here. So actually this is not equals to 0, but minus pi over 2 because of this equation, but it is considered 0 phase. So there will be no delay at outputs. Okay, but I'm not going to be to go in detail on how to prove that. Okay, so whatever it is, so what will happen if we have a 0 phase system? You won't have any delay at outputs, right? So if let's say you have your yn, which is equals to xn on VOV with hn, and this hn is a 0 phase, so then no delay at output. Okay, we'll see some examples later. So what does it mean? What does that mean? Okay, so I'm just going to be quick on this one. So let's say we have input signal. So this is an input signal. So we have, if you look at this example, so actually we have a 2 frequency here. So what is this one? So you can see that there's a 1 sinusoidal signal. So it is a sine signal. So it starts here, and then so it completes somewhere here. Okay, and then we have another one which is a higher frequency. So this is another one. So it starts here, and then it's complete somewhere here. Okay, so and then we do the summation. So and then everything will start at this is at 0 and 0, and this is the peak is actually at n equals to 2, and the peak for the lower frequency is somewhere here at n equals to 26. So and then we apply this is the hn. Hn is actually equals to 1 over 3 delta n plus 1 plus delta n plus delta n minus 1. So if you want to plot that, so you start from minus 1, 0, and 1, and this is 1 over 3. So delta n plus 1, so here. So actually you have a 1 over 3 here, 1 over 3, 1 over 3. So this is actually an even signal or even system. Okay, this is an even system. So then, because this is an even signal or even system, so we know that this is a 0 phase system. So when you do this and then you convolve with this signal, right? Do convolution between these two. So this is actually the output. So there will be no delays. If you look at, observe at the peak, so that peak is still at n equals to 2. And that peak, this peak, is still at n equals to 26. Okay, no delay. But because there is a 0 phase, so there's no delay. But if we look at the magnitude, the amplitude, okay, the amplitude is here, it is 1.5. This is lower than 1.5. Okay, so means that what is the magnitude of this filter at those two frequency? So it is not equals to 1. So it is supposed to be less than 1, right? It is less than 1 because from 1.5 it becomes less than 1.5. So it should be maybe multiplied by 0.8, 0.9 something. Okay, because it is less. It is less. So we can read these outputs such that delay is equals to 0 because there is no shifting, right? The signal doesn't have it doesn't shift, but the magnitude is actually decreasing a bit, right? So that's why the magnitude is actually less than 1. Phase equals to 0. Let's see. I think there's some. So as the h omega is a constant value, differentiation to its result is actually a 0 value. So this is the TG. right? So it means that all frequency convolved with a zero phase system will have no time delay at the output. So in other words, if there is no delay at all, no phase distortion, because a phase distortion is if you have a delay, but the delay is different on different frequency, right? But what is the problem? The problem with a zero phase system is that it is not causal. This one, this is actually not causal. This is our HN. Because causality says that you shouldn't have any value at this point. At n less than 0, it should be everything 0. Okay, so when it is not causal, so actually it is a bit difficult to implement. So you cannot implement that because it will involve a future value. So if you are dealing with an online system, then of course, definitely you do not know what is the future value. So this is not a good system because it is not causal. It is not causal. In terms of delay, it is very good because no delay at all. At all frequency, no delay. But it is not causal. So let's look on the second system, so which is what we call a linear phase system. Okay, so what is actually linear phase system? Hn is a delayed symmetry or anti-symmetry signal. So still, we are looking at those 4 special type of FIR, the type 1, type 2, type 3, type 4 symmetry. But we're going to push, let's say this is a signal, this is a system. So we're going to delay it. So we're going to push this so that it will start at 0. Okay, we're going to convert this so that we can have a linear phase. So the phase is not 0. So what does it mean by linear phase? The phase is actually not 0. Zero phase, the phase is 0, delay is 0. But linear phase is you will have a delay, but it will be consistent on all frequency. Okay, so when it is consistent on all frequency, so means that we doesn't have a phase distortion. So that's our target. We doesn't want a phase distortion. Okay, because we doesn't want a delay on a different delay on each frequency. Okay, phase distortion is something that you can imagine that if you have a live telecast of let's say a live a football match, right? So there's 2 things coming in. One is a video, another one is audio. So we need to make sure that the audio and video align. So that's the audio is actually it is actually saying what is actually happening on that time. Okay, because if let's say the audio comes first and then the video comes a little bit later, so it will be a problem. Okay, if it is a football match, so if there is a goal, then the audio is already saying that there's a goal, but the video doesn't really actually the goal is yet to happen. So we doesn't want that. We doesn't want that. So if there is a delay, the delay should be the same, right? That telecast, if the delay is let's say 10 seconds, so the audio is supposed to be delayed by 10 seconds, the video is supposed to be delayed by 10 seconds. In that case, there is no problem with that. Okay, everything will be fine. So this is actually the concept of having a linear phase. A delay is fine, but we need to have consistent delay on all frequency. So how can we get that? So by having a symmetry or anti-symmetry, which is we are going to delay it so that it will start at 0. Why we should start at 0? So that we will have a causal system. Okay, that will be the solution. So instead of a non-causal system, so we delay it so that now we will have a causal system. So this is actually the 4 types of the FIR. So let's see one example here. Okay, so actually this is this example 3. So we are actually repeating the example 1. Example 1 is this one, the one which we have seen. In this example, we doesn't have any delay. So all the peaks are at the same position as the inputs. So what's happening here is just we are reducing a bit the amplitude, okay, but no delay at all. But then we do that again using this HN. Okay, and it starts at 0, at n equals to 0. So then it will be causal. So that it will be causal. So, and then in this example, HN is delayed symmetry signal, is a delayed symmetry signal with 9 samples. So we delay it by 9 samples. Delay. Basically, HN will remove all frequency greater than 0.5 pi. Okay. Thus, both frequency in XN will be preserved at the output. So this is actually, we did some design on this one, and then we come up with this thing. So what will it do? So it will remove frequency greater than 0.5. So, but in our example here, so we have a frequency of, this is a 0.25 pi, and then this is actually 0.02 pi. Okay, so these two frequency will be preserved because what will be removed is frequency greater than 0.5 pi. Okay, so then we will see that, but because this is a delayed symmetry system, so we will have a delay. So we can see that now the first peak is at 11. So if you remember, the first peak on our original signal xn is actually at n equals to 2. Okay, so and this one is supposed to be at 26. So because it's being delayed by 9 sample, so this is 9 sample delay. So then instead of having this first peak at n equals to 2, now it's being delayed so that we have it on 11, on n equals to 11. The same thing here. So we are having it at 35 because this is a 9 samples delay of the original at n equals to 26. So 26 plus 9, 35. Okay, so we can see that the output is n. What we know also is, so it will preserve everything. So that's why this is 1.5 amplitude. So it is still 1.5. So at these two frequency, the amplitude will be preserved, similar to original. So what happened is just, it is being delayed by 9 samples. Okay, so and it's not really a problem because the signal is still looks the same because the delay is consistent. The delay is consistent. If the delay is not consistent, so maybe we won't see this kind of shapes. So the shapes will be changed. Okay, because the delay is different on different frequency. So I'm going to show you one example which have a different a delay on different frequency. So this is actually what happened if we have a phase distortion. So at 26, so instead of having a peak, now we have a negative peak. At 2, so we should have a peak also here somewhere. It's supposed to be here, but then somewhere here. Okay, it's being delayed. The lower frequency and the higher frequency is being delayed at on a different number of delay. So it is still a sinusoidal signal, but the peak, the positive peak, the negative peak has changed. Okay, so then actually this is becoming a different signal. So we doesn't want this, right? So we doesn't want this because actually in most application, maybe it's not a problem, much a problem, but it will be a problem mostly on audio implementation, like producing music, those kind of things. because music is like a guitar sound and a drum sound, so the frequency is different. The frequency is different, so we doesn't want that the sound to be aligned at a different time, a different delay, so it will be a chaos. All right, okay, so any questions? So we're going to conclude that in this first part for today's class. So in the second part, so we will see more examples. So we'll see more examples. Okay. So, but what is the basic now here is in phase. So we will see the effect in time domain, some delay. Okay, you will see some delays, right? And we have seen a zero phase system which doesn't give you any delay, and a linear phase. A linear phase means that you're going to have a delay, but the delay is consistent on every frequency, on all frequency. So which is fine. Okay, so we will stop here, and we will start back at 5 minutes, right? For the second part of today's class. Okay, see you guys in